Okay, we have a ring of radius A, has a charge of Q distributed evenly over the ring. We want to know what is the electric field at any point on the axis of the ring. So first, let's draw a diagram for it. This is a ring. There's a charge of Q evenly distributed on this one, which means if I divide it by 2 pi A, remember the radius of this ring is A, this would give me a linear charge density. Now, to answer what the electric field at point B is, I'm going to pick a very small element of charge here. I will call it dq. Because it's a very small amount of charge, point-like charge, I'm allowed to use the Coulomb's law. But because its electric field is a vector, I need to complete this diagram this way. So I connect the dq to the point B, and we know that the force or the electric field would be in the same direction as this line. And so this would be dE as a vector due to this little tiny infinitesimal charge. Now, if I know what is this angle, which is possible to know, assuming that this point B is separated from the center of the ring by x, and of course the radius of this ring is a, then the distance between dq and point B, which is r, can be estimated as, using the Pythagorean theorem, would be a2 plus x2 to the power of half. We can also know that the sine of theta would be the opposite a divided by r, and the cosine of theta would be x divided by r. We will be using these two also quantities later. Okay, so the dE, the infinitesimal electric field due to this little tiny dq, will have two components. So we can break this vector based on this angle theta to two components, one along the x-axis, which I already aligned it with the axis of the ring. So we call it dE sub x. And then another one which is perpendicular, and it's, let's say, in the y direction. So I'm going to call it dE y component. Now, dEx and dEy components are connected to the magnitude of dE. And the magnitude of dE can be calculated from the amount of charge dq and the distance between point B and dq, which is r. Okay, now let's put them together, and then after that, we will create the proper equations for this problem. Okay, so now let's calculate the value of dE. So dE sub x would be the magnitude of dE times cosine of theta. Well, we know that the magnitude of dE is technically a constant k, a universal constant, Coulomb constant, dq divided by r to the power of 2, which one can replace it with x2 plus a2. We also know that the cosine is x divided by r. So I'm going to replace them all at once. So it becomes dq times k divided by, then multiply by x. We have 1r and 2r. That becomes 3r. So it becomes x2 plus a2 to the power of 3 by half. Then we will have a y component of the electric field. That would be dE sine of theta. And so this becomes k dq times constant a divided by the same, r to the power of 3, and that would be x2 plus t a2 to the power of 1/2 multiplied by 3. So it becomes 3 by 2. Okay, now we have the electric field component, X and Y components, for only this little tiny charge. Now, to understand what is the electric field due to the entire ring, I need to repeat this for a lot of little tiny charges next to each other's on this ring, and I have to calculate the X component and the Y components, and then I have to add all these electric fields due to these little tiny charges. So let's just do it. Now, what we have to do is we have to understand how much is this charge, and when we integrate over this, what we get. And so you can think about this charge density if you like. Now let's just go and first work on the x-axis component. Okay, so the electric field on the x-axis would be the integral over all these little tiny electric fields for the entire ring, which becomes technically the integral of k x dq divided by x2 plus a2 to the power of 3 by 2. Now remember that the only quantity which is changing here is the dq, and everything else is a constant in this integral. And so we can take it out of the integral. So k, the constant, x is the position of the point B, x2 plus a2, which is the radius, the distance from the charge from the ring to the point B to the power of 3 by 2, and then we have integral over dq. Now notice that when we integrate over dq over the entire ring, what we get is technically the charge over the entire ring. So this is technically the charge on top of the ring. And so the dE sub x then would be k dot x divided by x2 plus a2 to the power of 3 by 2 multiplied by q. Now for the y component, the problem is a little different, because if I pick a dq on one side, then the y component of the electric field would be in one direction. But if I go on the ring 180 degrees away and then pick another dq and exactly in the opposite, the electric field component would be exactly the opposite to this dE sub y. Now, for the case of x component, they just added together. But for the y component, they cancel out. So you can start from this point and you can claim that there is an axis you can define where when you calculate the dE sub y for this left side, there will be a counterpart on the right side, which creates a dE sub y exactly in the opposite, and they cancel out. So when you try to calculate the y component then will be two-part, dEy for the half ring in the left, plus the dEy for the half ring in the right side. And these two values are exactly the same, except they're exactly in the opposite direction with one negative sign. And so this becomes, so at the end, the total amount of E sub y would be equal to 0. And so this problem reaches this point that it has only one component, the x component, and the value of x component of the electric field would be parallel to the axis, would be parallel to this axis, axis x, and the value of that would be kx divided by x2 plus a2 to the power of 3 by half multiplied by q. Now, there are two special situations where you can test this result. For example, exactly at x equal to 0, when you are right in the middle of the ring. We know that for every one of them, there will be an electric field, and these electric fields will cancel out. And so we know that the electric field at the center of the string should be 0. Now let's try it. So if I put x equal to 0 in this equation, I would get e sub x is equal to k times 0 divided by 0 plus a squared to the power of 3 by 2 multiplied by q. And because a squared is not 0, this has a value, a finite value, which is 0. Okay, so that makes sense. The second place we can test is when x is very large. X goes to infinity. When x goes to infinity, x2 plus a2, I can claim that it become equal to x squared. When x is much, much larger than a, then x2 plus a2 is exactly x2. Okay, so I'm going to replace this x2 plus a2 as x2 in that equation. So let's just do it. So e sub x then would be equal to k times x. Then we will have x2 to the power of 3 by 2 times q, which will give us k dot x dot q. X to the power of 2 to the power of 3 half will give us x to the power of 3. It's the same x, so one x cancels one x here. And so we will have k times q divided by x2, which is exactly the same as the electric field of a point charge when you are far enough from it. And so this guarantees that the solution we found makes sense.